All right. Today we're going to talk about electric flux, which is the flow of field into or out of a surface. This is going to be analogous to that concept of magnetic flux we looked at earlier, where it's the amount of field piercing an area. So we're going to define the flux phi through a surface in a very similar way, where instead of the perpendicular component of the magnetic field piercing a surface, we're just going to do the same thing with the electric field. And for some conventions, if our surface is closed, meaning it has an inside and an outside, we'll say that fields that are exiting a surface generate positive flux sources, and fields that are entering a surface generate negative flux. That would be your sinks. So sometimes you'll see this formula written using a cosine theta instead of E perp. They'll write it as E cosine theta. I generally am not a fan of that because you have to remember that theta is the angle with the normal vector, and that's not necessarily the one you're given. So here's a quick visual on flux and what we mean by E perpendicular. So if we actually draw out our components of this field here, we see that this electric field, this part in purple right here, this parallel field, is not actually exiting or entering that surface. So since it's neither exiting nor entering, this little purple component doesn't do anything to contribute to the flux. So what we want is this component, which we call E perpendicular, and that's what's actually piercing the surface. So when we talk about flux, we have to be very careful that we're only taking the amount of field that's piercing the surface. And that can be entering or exiting. All we care about is just that component that's perpendicular to the surface. So if you're given an angle, you might have to do some trigonometry. So we have a quick ranking to kind of assess this here. So we have 4 different cases. We're given that the electric field magnitude and the loop area are the same in A, B, C, and D. And we're just going to rank the flux, meaning the net amount of flow, sort of through this surface. And this is a 2D surface, also called an open surface, which means that there's not really a well-defined sign for flux. So we'll just talk about the absolute value of that electric flux. It is a scalar quantity, so we're just going to rank that. So first thing we want to notice is we're just going to start from that definition of flux that says the flux through surface is just going to be the perpendicular component of the E field times the area. So we should say in our justification that we're really just going to rank E perpendicular. So we have more flux when E is more perpendicular to the surface. So we're just going to go in and we're just going to rank how perpendicular each of the E fields are. So let's draw E perp in each case. So our perpendicular component of that E field, it's just going to be whatever is perpendicular to the surface here. So this would be our E perp for this surface. This would be our E perp for the second surface. The entire thing is E perp for our third surface. And there is no perpendicular component in the final case. And we can kind of tell that since these surfaces are sort of living in a horizontal plane, we're really just ranking how vertical the E field is. So we see that D, there is no E field piercing the surface. And in A, there's a little bit of the field piercing. B, there's more of it piercing because it's more vertical. And C, the entire field is piercing the surface. So D has the least flux, then A, then B, then C. And you can see that because it's all about this vertical component. So the larger the perpendicular component is, the larger the flux magnitude. So now we'll derive an expression for some flux values. So we're just given various diagrams, and we're given that in each case, the field strength is E. So first up, we got a pretty basic case. We just have a circular loop of radius r. So we know that our flux is just going to be equal to the perpendicular component of the E field times the area. And if we look at this surface, well, the entire E field is piercing the area. I can use the full E. And the area, it's just a circular loop, so pi r squared. And again, with these open surfaces, there isn't really a well-defined in and out, so we can't really make a good we can't really distinguish between positive and negative flux. Right triangular loop with side length s. And in this case, we're saying the E field is out of the page. So if I think about that, you can almost think of like a side view. Your triangle here. That field is going to perfectly pierce it, sort of popping out of the page. So if I think about holding any sort of surface, our E field is going to point directly through it. So this is entirely perpendicular once again. And the area of a triangle is just going to be 1/2 times base times height. So we just get 1/2 ES squared. Because again, our loop is in the plane of the paper, and our field is perpendicular to that plane, so it's a perfect piercing again. Here's our same circular loop of radius r, except now our field is tilted at this angle theta. So if we go and try to draw our components again, I might break it apart like this. So I have this component right here. That's the part of the field that's not doing anything. So I'm not interested in this green component of the field. But what I am interested in is this purple component up here, which is going to be E perpendicular. And if we just look at our diagram here and sort of how the theta is defined, we see that E perpendicular is the opposite side of our triangle. So this whole thing, the hypotenuse, again, you can't have a larger field than E. Your perpendicular isn't going to be larger than the actual field magnitude. And since E is going to be opposite, we'll extract it using sine theta. So this is a case where we don't use the full field because the full field isn't penetrating the surface. So it's not E that's penetrating the surface, it's only E sine theta. And this is still a circular loop of radius r, so we still just use our pi r squared. This would be E pi r squared times sine theta. And again, we also can reason it has to be sine theta in this diagram because if theta is small, that is a flat E field, and that will not penetrate the surface. But if theta is large, that's tending towards a vertical field, and sine of 90 degrees is 1. So in the vertical case, you get full penetration with your E field. Then a sphere of radius r. So here's an example of a 2D surface, an actual 3D surface, because there's an inside and an outside. So we can clearly define this as a positive flux, because we see that there's a net sort of source inside this sphere, which will become important later when we talk about these closed surfaces. And this wasn't a case we could actually get with the closed surface for magnetic fields, because they looped in on each other. But here we see we have a 2D sort of sphere here, that's our boundary. And it looks like the field is piercing the whole thing. So once again, we can just say that flux is E perpendicular times the area, and it's the full field that's perpendicular. And this is a sphere, so we're not going to use pi r squared. It's not a circular loop, it's a sphere, and the area of a sphere, we just use the relevant surface area of the sphere. So we just do, I'm just deciding how to write this. Now let's just write it as E times 4 pi r squared. And I'll put a plus sign there because this is a case where the sign could actually matter. So notice that our field lines are exiting. So we say that's a positive flux. Now we'll do some proportions. Circular loop is placed in a region of uniform E field that's perpendicular to the plane of the loop. We're saying the current flux is phi. Determine the new flux through the loop under each of these changes. So again, that's just this case. And we're given, that's just this, nope. That is just this case where our entire field is perpendicular, which is actually the most common case. So we want to find the new flux through the loop in each of the cases. So what if the electric field is doubled? Well, again, we know that flux is E perpendicular times A. And if I double the E field, I'm also doubling its perpendicular component, and I'm not affecting the area. So this is just going to double the flux. Radius of the loop is tripled. So again, flux is E perpendicular A. And in this case, we're tripling the radius of the loop. So we have to remember how area depends on radius. And it's pi r squared. So a good rule here is, again, remember that area is quadratic with respect to length. So if I'm tripling the radius, that means I'm tripling the thing that gets squared. So my flux actually goes up by a factor of 9. Because by doubling that radius or tripling that radius, you're sort of tripling both dimensions of the loop. So you get 3 times 3 the amount of area to pierce. And now the electric field is oriented parallel to the plane of the loop. So again, there's 3 ways to sort of change the flux through a surface. You either change E, you change A, or you change how E and A are oriented. So in this case, we said, what if instead our E field is oriented parallel to the plane of the loop? So instead of piercing it, it just sort of skims the surface like that. And well, what's happening in that case is you're entirely taking away the perpendicular component. So instead of E perpendicular being the whole E field, there is no perpendicular component anymore. So the flux is 0. So again, this one's kind of tricky. We have to remember that if you change the angle to the point where it's entirely parallel to the surface, you don't get any flux. And one thing we might have to do is if you have a field that varies throughout the surface, you have to do an integral. So if we look at all of these cases we've done, they've had these uniform E fields that are the same everywhere. So I don't actually need to integrate to find the flux. But if your field varies across the surface, you do actually have to integrate. So what we do is we chop up the surface into a bunch of different area slices and just find the flux through each piece and add them up. So instead of thinking of just a single surface, we cut it up into patches, usually uh, either patches on a sphere or these little vertical strips if we have these rectangular loops. So, for example, if you have a field that's getting stronger as it goes to the right in terms of piercing this loop, so we have this E field that says it's going to vary with the x coordinate and it gets stronger and stronger. So I can't just multiply E and A in this problem because E over here is different than E over here. So there isn't a single value of E I can nicely use. So what we do is we're going to chop up the surface into parts where that field is constant over, and then we integrate. So it is important that we expand out this dA So that just is going to amount to figuring out what the dimensions are of the strips that you're breaking your surface into. So in this case, these rectangular slices have height h and width dx, so that would be your dA. When we set up this integral, we know that our field is entirely piercing the surface, but we have broken up our surface into all of these little patches with height h and width dx, and then we integrate. So let's try this. Our rectangular loop is placed in the xy plane. Its bottom left corner is at the origin, has a length L in the x and W in the y, and there's a electric field out of the page, which is increasing as you go to the right. So if we think about what this field is doing, we do know it's entirely perpendicular to this loop. So we have small amount of field over here. We'd have a larger field over here. We'd have an even larger field over here. And an even larger field over here. And it varies only with the x coordinate, so I know that at all these heights, they're going to have the same strength. So why do we need integration? Well, hopefully the picture shows it. But again, the field, we say that E perpendicular varies along the surface. So that means we can't just multiply E times A. We could if you actually did like an average value type calculation. That actually does work. If you found like the average E field along this loop, multiply that by the total area, that does actually work. But again, we have to break the loop into vertical strips. And then integrate. So again, what we mean by that is, let's just pick maybe this strip, for example, because the electric field is constant vertically. So we're going to break it up this way and sort of build as we go across. And notice that this is going to be a really small width, dx, and this is going to be that height, w, of the loop. So our tiny little area slice is going to be the width of the strip times dx. All right, so let's find that total electric flux through the loop. So we can't just multiply E perp and A in this case because it's varying. So I have to sum up all of the flux contributions of each of these strips. And our expression for E was A times x squared. And that's entirely perpendicular to the loop. So I can plug that in. I don't have to do any trigonometry. And then we said dA, well, our strips have width W and length dx. And then we look at where our strips are actually spanning. So our first strip starts at x equals 0, and we go all the way out until x equals L. And notice A and W are constants. And then we just do a simple power rule on this. So this is x cubed divided by 3. And then we work that out. And since it starts at x equals 0, we don't have to deal with that lower limit. So we get AWL cubed over 3. And again, this is a 2D, or sorry, this is just like it's an open surface, so it doesn't really matter what sign we use. Not too many like variations of this problem. You're just going to have some expression that you have to integrate, and it's usually the technique of chopping up into these strips. So if you can find the strips where the field is constant, Do it that way. All right, now we have a closed surface. So consider a cube of side length S, whose bottom left corner is placed at the origin. In this region, there's a constant E field in the x direction. So if we draw ourselves some field vectors here, let's use the line tool. We get something like this, and the field is constant. So draw this vector field and justify that the net flux through the cube is 0 without using equations. Well, just based on this picture, we said the flux, that's the net flow into or out of the surface. And just based on this diagram, we see, similar to like one of the ways we justified Gauss's law for magnetism, we see that all field lines that enter the cube exit with the same magnitude. So what that means is that phi into the surface equals phi out of the surface, which means that there's no net flow in or out. So just because field lines enter and exit doesn't necessarily mean the flux is 0, but here there's no change in value. So everybody that enters also exits. Verify our claim by finding the flux through all 6 faces and taking a sum. So we can actually simplify our work a lot here just by using symmetry. So if we look at this cube, we see that the field is pointing to the right at all points. So what that means is that the rightward field is only going to pierce faces of the cube that are entirely perpendicular to that x direction. So if we actually look at our cube, there's only 2 faces that contribute to the flux. So we have this face when the field lines exit, and then we have on the other side the face where they enter. So, because if we try to look at, for example, the top face, we see on the top face, an electric field just sort of skims that surface, so it's not getting pierced. Same thing with the bottom, and same thing with the sides of the cube. So, first of all, we see that phi equals 0 along 4 faces. That's going to be top, bottom, front, and back. And that's because in those in those faces, there is no perpendicular electric field. So again, just going back up to summarize that, we said that nothing pierces the top, the bottom, front, or the back. So now we can just work it out for the left and right faces. So phi on the left face, we see that the left, this is where the field lines enter the surface for the first time. It's that left face is where the lines enter. So we know it's going to be E is the field strength. The area of one of the cube faces is S squared. And this is into the surface. So we say that flux is negative, because that would be a sink. And then if we do phi from the right, it's a similar story, except this is where the field lines exit. So we see that as expected, our net flux through all 6 faces is going to be 0. And I'll even go the extra step of like showing we actually did look at all 6 faces. So I could even say phi net is 0 plus 0 plus 0 plus 0, the four faces that did not contribute. Then I had a minus ES squared, and then I had a positive ES squared, and that's 0. As expected. But to conclude, we'll show that this isn't necessarily true in general. So let's say more specifically, we have the same cube of side length s, except it varies as a function of x. So we can check our two like main values of x that we're going to be interested in here. So if we check e of 0, that's going to be e times 0 plus 1 times I hat, which is just equal to e times I hat. And then if we check e at s, this is going to be e0 s plus 1 times I hat. And we'll probably just leave it like that. So we see that our field is actually going to be increasing because we have E, and then we have E times S plus 1. So again, this is where we get our original field, so we're just adding on to that. So if we draw this, we could get maybe show like a small field is going to enter, and a larger field is going to exit. So justify that the net flux should not be 0 for this cube. Well, we see that E increases from left to right. So this means that phi out of the surface is going to be greater than phi into the surface, which means the net flux is not 0. Just based on this picture, we see that, well, I have more field lines exiting than entering, so there must be some sort of source inside. So on average, this should be a positive flux. Let's figure out what that is. So once again, phi equals 0 for top, bottom, front, and back. Because again, that flux wasn't 0 because of the uniformity in the previous part. That part was 0 because there was no perpendicular. So I don't care how the field is increasing left to right. For those faces, it's still not piercing the surface. So what that means is that we can now just go ahead and deal with the left and right face. So phi, the left face is going to be E on the left face times S squared, and that is once again a sinc. And going back up here, we said E at this left face is just called E. So we get negative E S squared once again. And then phi for the right face is E on the rightward face times S squared. And that's an outward flux. And E for the rightward face, we said was E times S plus 1. And now we can work out our net flux. So let's work it out. So our net flux is going to be negative ES squared plus E times S plus 1 times S squared. So, of course, let's work out what this is. So we get this whole quantity here. This is going to become S cubed plus S squared when we work that out, right? Because you got to distribute that S squared in. So we get ES squared plus E times the quantity S cubed plus S squared. That's going to be negative ES squared plus ES cubed plus ES squared. And now we see the ES squared terms cancel. So I'm just left with quite a simple result, actually. It's just positive ES cubed. So we do get a net positive flux, which is what we thought we'd get. And now we'll try to connect this with point charges. So we had like a connection between magnetic fields and the flux because we said these bar magnets or just any sort of magnetic field always had this like curling back around effect. So we knew there's never going to be a net flux through a surface. But all this sources and sink stuff should probably connect to what we said sort of when we defined electric fields, that positive charges are sources and negatives are sinks. So if we figure out how much flow is in a surface, that should definitely depend on the charge inside, among possibly other things. So let's first justify why this should exist. So we'll begin here by drawing a point charge electric field. So let's say I have a positive charge and I want to consider what that field looks like if I draw a sphere of radius r. So maybe let's draw the sphere first. Again, if I try to draw myself a little sphere here and I put my positive charge in the center of it, we said that positive charges are sources of field lines. So sources and sinks are going to say that we get something like this, where our field lines point out of that charge. And just to avoid clutter, let's just show what the field looks like kind of on that spherical surface. So at the top of the sphere, points out. At this angle, points out, and so on. We can see that by defining these electric field lines from positive charges as it's a source, meaning it points straight out, we see that it has this radial symmetry. Again, it being radially symmetric tells us that E has spherical symmetry. And why that's important is if we look at our expression for E from a point charge anyway, we see that the magnitude of E from a point charge is just K times Q over R squared. And we actually dealt with the direction already. That's that R hat. So we see that that's why the field lines always pointed out. So what this means is that our net flux is just going to be equal to E times A. So that's why we like it. That's why we like drawing this sphere, and this problem is going to work out nice, is because phi is just going to be equal to E times A, because the entire field is perpendicular, and it has the same magnitude everywhere on the sphere. Because the only thing that affects the magnitude is R. And by definition, a sphere, that's all the points at that same R, that same separation. So let's verify that this flux is constant regardless of the sphere radius. And this is definitely not intuitive at first. You would think that if I have a bigger sphere, well, that's more area. So that should definitely have more flux because it's a bigger area being pierced. But then you might also argue, wait. If I have a bigger sphere, that means I have a bigger distance, and E shrinks with distance. So, is it bigger? Is it less? Well, actually, it's constant. And we'll reason through that after we derive it real quick. And this is a huge result. This is one of the four Maxwell equations, uh, and we're going to prove a special case of it. So, we said that flux, in this case, could be written as E times A, because our field has the same magnitude everywhere in the sphere, and it's always radially symmetric, so I don't have to do any trigonometry. And E at the location of the sphere is going to be kq over the sphere radius squared. The area of a sphere is 4 times pi times the radius of the sphere squared. So now we see what we kind of talked through, that yes, it's true that the area increases quadratically, but the field shrinks inverse quadratically. So we see that if I work that out, we get, well, the r's cancel, so I get 4 pi times k times q. And we can actually simplify this even further, because we can remember that this Coulomb constant k is defined in terms of the permittivity of free space as follows. So we get a 1 over 4 pi. So we get 4 pi times 1 over 4 pi epsilon naught times q, which is just q divided by epsilon naught, because the 4 pi's cancel. And notice this is not a variable expression. So I could draw as big of a sphere as I wanted to, and I still get q over epsilon naught as the flux. And the little thing I added here, which is a bit more subtle to prove, is that it actually doesn't have to be a sphere. I could have drawn whatever shape I wanted to and still gotten q over epsilon naught as the flux. So the trick to kind of proving this fact involves slowly deforming the sphere and showing that if you take sort of the projections of this newly deformed area, well, when you extract the component that's actually getting pierced by the field, you actually recreate the sphere. And again, the real like importance of this argument is that flux is constant because area is quadratic with r, but the field is inverse square with r. So the fact that you have a larger surface is exactly balanced by the fact you have a weaker field, because they have the same dependency on r. And this is known as Gauss's law for electric fields, is that the net flux through a closed surface isn't zero, but it's actually directly proportional to the enclosed charge. So if you figure out whether there's a sort of net source or sink that your surface is acting like, you can figure out if there's a net amount of positive or negative charges in it. That's not possible for magnetic fields because there are no magnetic monopoles. So that's a pretty big result that we're trying to gain some intuition behind for this. So yeah, that's our introduction to flux.